perhaps we will not post this video. Okay. Dr. Lee, you recorded? Okay. All right. Okay, so it is a rainy day. And those of you that are watching on video are lucky that we are posting this video after several students did not come to class. Okay. As I promised, I think today's lecture will be a little shorter because you probably have an assignment to finish. Or are you done? Are you done with assignment 3? No? Almost. But after today, we are done. No more assignments. No more grading. Okay. So what I wanted to talk about today was actually about memory. Because in this class, we've talked a whole lot about, even though the class is called parallel programming, I feel like all the time I'm talking about communication, not about parallel programming. And that's because moving data from memory to a processor, or moving data maybe from one processor to another across a machine room is very, very expensive. And we talked about expensive in 2 different ways. I said it was expensive because it was slow, meaning that there was low bandwidth between memory and the processor. And I also said it was expensive if you care about energy. If you're writing mobile applications, data center applications, or supercomputing applications, you care about energy. And at one point, we talked about how it could be hundreds of times more energy to move data from memory to the processor than it is just to compute, to do math on the data once it's in the processor. So, well-written programs, and we have talked about many examples of well-written programs. Well-written programs will try and move data from memory to the processor's storage, like a cache, once, and do as much work on the data as possible before the data goes back out to memory. And you are probably tired of me talking about this, because I've shown you this slide in class 5 different times about reorganizing a computation so that we reuse the data multiple times. I did the exact same technique when I was talking about image processing, where instead of writing a whole image and then reading the whole image back in, I created a little piece of the image and then reused it immediately. Reordering the computation was the whole point of the Spark lecture, about how we write code as if it looks like arrays, but we actually execute it in a simple order where there's very little traffic. And then on Monday, I talked probably for 10 minutes about how to order matrix multiplication and convolutions. And none of this talking, all of these examples, none of them were about parallelism. They were all about reordering the computation to minimize the amount of data that I need. So the reason why we did these things is we wanted to put data in cache, because it's fast to access in cache. And I wanted to point out that there's two types of storage that is on a processor. The first one is a cache, very much like you're familiar with. Like an Intel processor has L1 cache and an L2 cache. And a cache, if I took the caches out of a processor, your program would still run. It would just run more slowly, because your program does not know caches are there. The program just reads and writes from addresses, and sometimes the computer chooses to copy the data and keep the data out of memory. The data at some address that's normally stored in memory is actually stored in cache. So if I go back to the code on the previous slides, let's look at some code. Well, this code is written in order to keep the temporary buffer in cache, right? And this code here is written so that the intermediates here might sit in cache. But notice that there's nowhere in this program that says put data in the cache. This program just reads and writes from these addresses, and they happen to be in cache. So a cache is just an implementation detail. It's something that a computer architect has built to make your data accesses go faster. The computer architect says, well, if you access the same data twice, the second time I will make it much faster. And since you know a computer has that property, you can change your code so that many of the accesses will be in cache. Now, another way to put data right next to the processor is not to make a cache, but to build what is often called a Scratchpad. So a Scratchpad is still storage right on the chip. But that storage is not a cache. So I'll give you 3 examples on this slide. And the first one is, let's say, is CUDA shared memory. CUDA shared memory is storage that's on the chip. It's hard to see, but this is the block of 64 kilobytes of shared memory. Shared memory is implemented with really fast storage that's right on the processor, just like a cache is really fast storage, just like on the processor. But with shared memory, if you used it on your assignment, you had to yourself load data from memory into the storage before you could use it. So a Scratchpad is a separate address space where all of the data in that address space can be accessed very quickly because the address space is implemented with very fast on-chip storage. So a cache does not create a new address space. It is an acceleration of main memory. A Scratchpad is a completely new place to put data, and it's implemented to be very fast. So CUDA shared memory is an example of a Scratchpad. This was a processor with 8 cores, and this was the processor that was in the PlayStation 3. So this is called the IBM Cell Broadband Engine. So this is the PlayStation 3 processor. So it had one regular CPU, like a normal CPU core with caches, and then it had 8 little cores. And those cores did not have caches. They only had 256 kilobyte Scratchpads. So to program the processor, you had to load data into the Scratchpad, just like you loaded data into shared memory in CUDA, and then you can run computations on that data. And this is the block diagram of the cores in the Sunway processor that's in Taihu Lite. And there's 260 of these cores per processor. And each one of the cores does not have an L1 cache. It has an L1 instruction cache, but you can't load and store data from that cache. The cache is just for your instructions. It only has this thing called SPM, and SPM stands for Scratchpad Memory. And so if you program the Sunway processor, you will load data into the Scratchpad memory. You will issue an instruction which says, load data from main memory into the Scratchpad. And then all of your adds and multiplies and code will run on data that's stored in the Scratchpad memory. So it's much more manual. Whereas if you write code on a CPU, you're like, well, I hope this data is in cache. When you write code on a Scratchpad, you say, put this data in the Scratchpad, because when I access it, I know exactly how fast it would be, because the Scratchpad is all on chip. So there are 2 ways of the processors, the computer hardware architects can build very fast SRAM storage and put it right on a processor. Okay. But I'm going to talk today, so I want to talk a little bit about something that maybe a lot of you, especially if you're computer scientists, may not be aware of, which is how DRAM works. So up until now in this class, we've said a processor asks memory for data. So the request goes over to Mr. Data, to Mr. Memory, and the memory says, okay, here's the data. And we assume that there was some amount of time that that took. But memory, just like a processor is complex, memory is pretty complex too. So if this is a very simple CPU, let's just say it has one core, that core has a couple of caches, or maybe Scratchpad memories. And what's important is what the last level of cache is. So on an Intel processor, the last level of cache is usually an L3 cache. So I'm drawing, let's say, the L3 cache. And if you miss the L3 cache, if a memory address is not, if a value is not in the L3 cache, well, then the processor needs to request it from memory. And there's a unit called the memory controller that is responsible for making these requests out to memory. So my simple diagram here is there's memory, there's a processor core, there's caches, and then there's a unit called the memory controller, which is responsible for asking memory for data when the caches do not have it. So I usually have drawn memory, or DRAM, as a big box with no other detail. So now let's look inside what's in that box. So here is sort of the simplest unit of how a DRAM chip works. And DRAM is, if you can think about it like a big array. This almost looks like a photo sensor in a camera where all of these are pixels. And that's almost what it is. So a DRAM chip has a 2D array of capacitors. So every capacitor can hold charge. And if it holds enough charge, well, that's storing a 1 bit. And if it doesn't have enough charge, it's storing a 0 bit. So this is my DRAM chip, and it's an array of capacitors, and it's organized into rows and columns. And in this example, I have 2,000 bits, 2 kilobits per row of the DRAM. And then I have, down here, I have 8 data lines, or 8 wires, connecting this DRAM chip back to the processor. So this is the memory bus. It is an 8-bit memory bus. So these wires go back to the processor. All right, so let's say that we wanted to read 1 byte of data, 8 bits, from this DRAM chip at that location. So those 8 capacitors hold the 8 bits that the processor wants. And so there's a process that I have to go through to read the charge in those capacitors, turn it into a digital signal, and send that information back to the processor. So let's think about this. So the first thing is an operation called pre-charge. So running down every column, in the DRAM chip is a wire. And that wire, what we're going to do is we're going to read the charge, the voltage in a capacitor, and that's going to change the voltage on the wire that connects up to the capacitor. So it's going to hook a wire up to the capacitor is going to bleed charge out into the wire, and that's going to make the voltage on the wire go up or down. And then we're going to read that voltage down here. So pre-charge is setting all of the wires to a fixed known voltage, because then we're going to look to see if the voltage goes up or down. And then step 2 is called row activation. And row activation is basically hooking the capacitors on one row of the DRAM chip up to these data lines, up to these wires, so that the charge bleeds off into those wires. So now every one of the wires has charge that's proportional to how much charge was in the corresponding capacitor in the currently active row. So the information now flows down to the bottom of the chip. So all of these wires now have charge on them. And then down here at the bottom of the chip, there's an analog to digital converter where I can turn those wires, I can turn that charge into bits, into ones or zeros. So down here I have storage for 2,000 bits, 2 kilobits, which is a copy of the data in the active row. So this is the first point we have actually moved back to digital. Everything up until now is actually all analog. So now we're digital. So this is called the row buffer. This is a buffer that stores a digital readout of what was in one of the rows. So step 1 is prepare the wires, pre-charge. Step 2 is activate a row, read the charge, and convert it to a digital signal. Step 3 is figure out which byte in the row buffer we want to read, which would be this byte right here, because that corresponds to the bits that we wanted. And then step 4 would be to transfer the data in this storage out over the data bus to the processor, like this. So just to recap, to actually read memory, what a DRAM chip will do is it will pre-charge its bit lines, connect them up to a row, activate a row, read the charge in the row down to the row buffer, and then select the appropriate byte in the row buffer to transmit over the memory bus back to the processor. That's what it takes to read a byte of data from the DRAM. Now, if you have spatially contiguous memory accesses, let's say now we want the next byte of data in memory. Well, we don't have to do steps 1 or 2 anymore, because we already have a whole row of data down in the row buffer. So the next byte of data is much quicker. We just move over and read the next byte of data. So the cost of accessing memory, we used to think about it as dependent on whether or not you hit the cache or whether or not you went out to memory, to DRAM. But really, the cost of accessing memory is whether or not you hit the cache. And if you go out to DRAM, it's whether or not you hit the row buffer or not. So the access latency to DRAM is actually not fixed either. In the best case, the byte that you want to read is already in the row that's in the row buffer, and we just have to read the row buffer. The worst case is we have to go through all of the steps that I just discussed. We have to pre-charge the bit lines, activate the row, copy the data in, convert the data, or put the data in the row buffer, and then read the row buffer. So the memory controller has to decide sort of how to issue some of these operations. Like, here are some examples. So one question would be, when does the row buffer execute this pre-charge operation? So the pre-charge operation takes some time. And on my previous slide, actually, I had the amount of time it took. It takes about 10 nanoseconds to do pre-charge, another 10 nanoseconds to do row activation, and another 10 nanoseconds or so to read the row buffer. Right? So it might take up to 30 nanoseconds, which if we have a 1 gigahertz processor, that's 30 cycles of latency. Or it could take 10 or less cycles, depending on what the state of memory is. So one thing you could do is you could say, you know what, DRAM, every single time it completes a memory operation, it should go ahead and pre-charge the bit lines to get ready for the next one. Or it could say we should wait. We shouldn't reset the bit lines, because hopefully the next access will be to the same row. So there's a scheduling question. If you think you're going to have high spatial locality, you probably don't want to pre-charge the bit lines. You want to wait and make sure that the next access is to a different row before you get ready. What most DRAMs do is they will wait and assume that the next access is to the same row, because usually we access entire cache lines, 64 bytes. So there's continuous memory accesses. And then there's the question of, well, you should be concerned right now, because you're like, oh, look, if DRAM takes 30 cycles to access the data, and then transmits it over the bus in that byte in one cycle, the bus is only busy 1/30th of the time. That's not good. It's very inefficient. Is there any way we can do better? Okay, so let's look at some ways that we can do a little bit better if we work for a company that made DRAMs. Okay, So here, what I decided to do is I gave you four different bytes that we're accessing from DRAM. So this is a sequence of commands. The memory controller says, I want the blue data, then I want the orange data, then I want the green data, then I want the purple data. And notice, this is how memory will react to that stream, and hopefully it makes sense, right? The first access needs a pre-charge, row activation, and then column activation. The next access only needs a column activation, and why is that? Why did I not do row activation or pre-charge for the orange memory access? Because it would be the same rows right next to each other in the address space. And then of course I moved to a different row for the green and a different row for the purple. So, okay. So if every time I read data, or sometimes I read data, I have to pay the penalty of pre and RAS, there's some things I could do to lessen the cost of that penalty. So one thing would be to say, DRAM does not return bytes of data, even though it can only return 8 bits at once, because that's what the bus size is. Well, we can send DRAM a command which says, you know what, DRAM, I want 64 contiguous bits of data. So you could put the DRAM in a mode where you ask for much larger chunks of data at the same time. Right? So DRAM will say, I will do the pre-charge, I'll activate the row, and then over the next 8 clocks, I will give you 8 bits, and then another 8 bits, and another 8 bits, and another 8 bits. So it'll be much more efficient. So this is called burst mode DRAM execution, which is pretty obvious, right? Like if the granularity of transfer is too small, we'll make it bigger. No problem. Now the next thing that these DRAM people do is they take this is one DRAM array. And then what they do is they put, well, let me ask you a question first. So in this class, especially when we were talking about processing, if an operation had latency, let's say 20 nanoseconds of latency to get ready to read, and we had a bunch of parallel requests, what was the technique that we used to hide the latency? We used pipelining or multi-threading. Right? So when this thing was busy, let's go do something else. So that's exactly what the DRAM architects are going to do as well. They're going to take this array, this is the storage unit, and they're going to make a bunch of copies of it. Or not copies, so they'll have multiple versions of the array. Now each bank, so they call these banks, so you can think of it as memory bank. It holds your data, just like the bank holds your money. And now there are 3 memory banks on this DRAM chip. So each of the banks holds different data, different addresses. So this memory chip is now 3 times more storage than before. But now, each of the banks can be pre-charged and row accessed in parallel. So here's a timeline of operations of what each bank is doing. So time is going this direction. So at t equals 0, we pre-charge bank 0 to start a read from bank 0. And while we are waiting for that to finish, we'll send a pre-charge command for a different memory address to bank 1. And while we're waiting to bank 2. And so when bank 0 is ready, we'll send this byte over the memory bus. A little bit later, bank 1 is ready, and then this byte goes over the memory bus. And then a little bit later, this byte goes over the memory bus. So in the processor multi-threading example, what were we trying to keep busy all the time? We were trying to keep the processor's AOUs busy all of the time. That was the idea of threading or pipelining the operations. Here, what are we trying to keep busy all of the time? The memory bus, because this is the smallest connection in the system. It's the small highway or the small road between memory and the computer. And so if this is the scarcest resource, we better be very efficient about how we use it. So you want to use it all of the time. So we're using pipelining here to try and keep it really busy. So if the smallest unit of storage is a DRAM array, then we make multiple DRAM arrays that we call banks that can be accessed in parallel. And then this is a DRAM chip. A DRAM chip has multiple banks. So for like if you go to Micron or a memory company and buy a DRAM chip, it will be a chip. The specifications have multiple DRAM banks, and there's 8 data pins coming out of it. So you can imagine that data pins in communication are very expensive. These are very easy to build. In other words, like there's basically a transistor per capacitor. And that if you want more memory, you'll take multiple DRAM chips. In fact, you'll take 8 of them, and you will stick them together into a DIMM. DIMM stands for Dual Inline Memory Module. So for any of you that have opened up your computer and added memory, you probably have bought a DIMM and stuck it right into your motherboard. So a DIMM, in this case, has 8 DRAM chips. 1, 2, 3, 4, 5, 6, 7, 8. Each of those chips have 8 data pins. So the width of the memory bus to the DIMM is 64 bits, or 8 bytes. And so the memory controller communicates with the DIMM and sends commands that say, read bank B, row R, column 0. So the memory controller does not say, I want address 0x blah, 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 blah. It says, I want the data in bank B, row R, column 0. And all of the DRAM chips take the same command and will return to the DRAM controller 8 bytes of data that happens to be at B, R, 0. So altogether, this command actually accesses 1 byte of data from all 8 DIMMs, which gets back 64 bits, or 8 bytes of data from memory. So notice that this is one command. The same command is sent to all of the chips. Sometimes you see DIMMs that have 9 chips. Has anybody seen a DIMM? Those of you that open a computer up, have you seen one with 9 chips? So do you know what the 9th chip is? What is the 9th chip? It's, do you know what ECC means? It's the error correcting code. So the data is replicated in one of the chips, so that you get 1 byte is the error correction code on memory. So in case any of your memory goes bad, you can detect that memory is bad and correct that code. So you're going to burn 1/8 of your memory capacity in order to perform error correction. And that's very important. Like any big computer these days will have the ECC error correcting memory, because if you're like Taihu Lite and you have, I can't remember how much memory it has, but it has terabytes on terabytes of memory. The probability that one of your bits will flip incorrectly, just randomly, is incredibly high. Like it happens once an hour or more. So you need error correcting codes to detect when a cosmic ray has hit Taihu Lite and changed one of the bits in memory. So let's think about reading one 64-byte cache line from memory. So on Intel processors, cache lines are 64 bytes. So that the memory controller will always ask for, please give me 64 bytes of data. Because the granularity of moving data from the CPU to from memory to the CPU is always exactly 1 cache line. So the memory controller always asks for 64 bytes of data. Now, we can only transfer 8 bytes of data at a time, because the memory bus now is 64 bits. So let's say that we do the obvious thing, the very obvious thing. The obvious thing is that 64 bytes of data should be, that are next to each other in the address space, should be next to each other in the same row of one div. Makes sense, right? Like we have a 2 kilobit row that is 128 kilo, sorry, it's two kilobits, so that's 256 bytes. We want a cache line, it's only 64 bytes, so that should all be on one row of one div, right? So let's think of, if we do that, let's think about how this system will access the data. So we say, and let's say that that address is stored at bank B, row R, column 0. Right? Because I can maybe take the memory address, divide it by the number of bytes in a bank, divide by I just do 3 divisions and I can get bank, row, and column. Okay. So in the first clock, well, the first thing we'll do is we'll wait. We'll activate row R on bank B. We'll read the appropriate column, which is 0. That's here. And at the first clock, 1 byte gets transferred. Now, why did I say that the other memory chips transfer byte, the byte at bank B, row R, column 0? But it's not very useful, right? Because the 64 bytes that I care about are all right here on this one DRAM chip. So the other transfers, I don't care. I don't want those addresses. And then in the next clock, I'll get the next byte of the cache line. And in the next clock, I'll get the next byte of the cache line. So how many clocks would it take me to get the cache line, given this mapping of memory addresses to DRAM chips? It's a 64-byte cache line. I get 1 useful byte per clock because all of the data is on chip 0. So it takes me 64 bytes, 64 clocks to get all the data. And I'm using only 1/8 of my memory bus. So can you think of a better way to map addresses in the address space to the DRAM chips so I can use all 64 data pins much more efficiently? How can I map addresses to chips? So my first solution, which wasn't very good, said that I'm going to take contiguous addresses and I'm going to put them all together on a row of one chip. Or in other words, I'm going to take all, if this is a 1 gigabyte memory, I'll put the first gigabyte of the address space here, the next gigabyte of the address space here, the next gigabyte of the address space here, and so on and so on. But is there a better way that allows me to use my memory bus perfectly if I'm reading the cache line? How would you do it? Okay, so you say equally, and what do you mean by equally? Because I did it equally too. I put the first addresses 0 through 1 gigabyte here, addresses 1 gigabyte to 2 gigabytes here, 2 gigabytes to 3 gigabytes here. So mine was equal. What do you mean by equal? So where would you put byte 0? Let's put byte 0 here. Now where would you put byte 1? Now we're going to put byte 1 at bank B0, row R, column 0. But we're going to put byte 1 on chip 1. And then byte 2 on chip 2. And byte 3 on chip 3. And so on and so on. And where will byte 8 go? Well, let's say we'll put byte 8 will actually be bank B, row R, column 1. Right? So if we interleave the bits of the bytes of the address space over the chips in the DRAM now when I say read bank B, row R, column 0, what do I get? I get the first 8 bytes from memory, and they're all the bytes that I want. And now reading the cache line from memory takes how long? 64 divided by 8, so it takes 8 clocks to get the data. And of course, there are other interleaving patterns that would also be equally efficient, right? I could have put 8 consecutive bytes here, the next 8 bytes here, the next 8 bytes here, and I still could have gotten the cache line in 8 clocks. So there are different possible interleavings. So the first clock, I get the first 64 bits, right? I get 8 bytes. The next clock, I get another 8 bytes, and so on and so on. So I think you guys all see it. So the memory controller, which up until now in this class I hadn't even talked about. I just said the processor asks memory for data. Really, the processor is asking the memory controller for data. And the memory controller is asking memory for data. And the memory controller is actually pretty sophisticated, because the memory controller sees all of these requests from the processor. And the memory controller knows about what state DRAM is in. So the memory controller, first of all, translates address X to row, bank, column. And the memory controller will often have queues where the memory controller buffers all of the requests from the processor. Like the processor says, I want address X, and I want address Y, and I want address X plus 1. And the memory controller will do very complicated scheduling to make sure, or to try to use the memory bus as effectively, as efficiently as possible. So for example, it may sort the requests by which memory bank to go to. So it can issue commands to different memory banks, because it knows those can be done by the memory in parallel. The memory controller knows what the last request it made of memory was, so it knows what row is currently active. So it might try and re-sort the requests so that they actually, so multiple requests to the same row happen one after another. And a common policy is what I have here on the slide. It's called FRFCFS. And this is the kind of the baseline scheduling policy in a memory controller today, which is called, FR is called first ready, first come, first serve. So what that means is that the memory controller will, if it receives a request, it will always process requests to the currently active row first. So if any of the addresses map to the active row, those get to go to the front of the line. And then for all other addresses, it will just be first come, first serve. It will be FIFO. It will be in the order of arrival. And there's a lot of active research these days on other algorithms that improve on FRFCFS, especially when there are multiple processors and things like that. So you could go read many papers about algorithms for how to schedule memory requests. So a sort of funny thing that's happened is that, remember that I said that the idea of parallel processing was to make many really simple cores. Take all the complicated scheduling and out-of-order logic out of the processor. Well, really what's happened is we did that, and we made all of these really simple cores. And now all of these really simple cores are at the same time asking the memory controller, please give me data, please give me data, please give me data. And so all of the complicated scheduling ended up in the memory controller now. So it's not about scheduling instructions in an instruction stream. It's about scheduling all of these memory requests. So a modern processor, like a CPU or even a GPU, like a GPU has thousands of CUDA threads running at the same time. The scheduler in a modern GPU is actually scheduling thousands of different memory requests. So it's a pretty sophisticated thing. So okay, so far we know what a DRAM, we know what a DIMM is. We know what a memory module is. And if I want more memory, if I want more bandwidth than just 64 bits per second, I can actually connect multiple DIMMs up to different memory channels. So if you hear, when you're reading about your processor, if you hear like the marketing materials say dual channel memory, Well, that means that the memory controller, there's basically two memory controllers. Or there's a memory controller with two completely different channels to two different DIMMs. So the memory controller can send commands to this DIMM, read this row, read this bank, and in parallel can send commands to the other DIMM. And they can be completely different rows or banks and so on. So that's a dual memory channel. So I went onto Intel's website and looked at the specification for a processor that was recently purchased for one of the computing labs at CMU. So we bought this particular Intel processor, Xeon E5 G4. That doesn't matter, and if I go on the Intel website, you can get the specifications for that processor. So the maximum memory size would be 1.5 terabytes. The memory controller can address up to 1.5 terabytes of memory if you happen to want to put that in your computer with one core. So the memory type is DDR4. It stands for double data rate 4. And the memory bus is at 1.2 gigahertz. So the clock of memory is at 1.2 gigahertz. So what that means is that, remember, there's a 64-bit memory bus. That's what connects up to the DIMM. It can send data, 64 bits, at 1.2 gigahertz. It can actually send data twice per clock, which is a detail that doesn't matter too much, but I'm going to multiply the bandwidth by 2. And the 2 bytes per clock, running twice per clock, is actually the reason why it's called DDR. DDR stands for double data rate. So sending information twice per clock is DDR. So every memory channel, 64 bits times 1.2 gigahertz times 2, gives me 19.2 gigabytes per second. But notice that this says that this computer, this processor, can be hooked up, if you want, to 4 memory channels. And so if we use 4 memory channels, each at 19 gigabytes per second, well, that's 4 times 19, and that's 76.8 gigabytes per second. And hey, look, if I look up the specifications at Intel, the maximum memory bandwidth is 76.8 gigabytes per second. So now you should be able to decode these spec sheets when you read them. This particular memory for DDR4 is about 13 nanoseconds to do a column access. So every time you want to read 1 byte from data, that would be about 13 nanoseconds, which is actually, the clock is a little bit over a gigahertz. So 13 nanoseconds is roughly what? Is roughly about 16 or 17 clocks. So you can only read 1 byte per clock unless you're using 1 byte per clock per chip. So 8 bytes every 17 clocks, unless you're using like a burst mode transfer or pipelining across the different banks. Okay, so that's how DRAM works, which is kind of fun sometimes to learn that there's a lot of complexity in just asking this question, please give me this data. Like I said earlier, there's a lot of research in how the memory controller can schedule all of the memory requests so that the memory bus is used as much as possible. Okay, so the first idea today was how memory works, but really the first idea was that if we want to use memory efficiently, we have to change our algorithms so that the memory, so we have high locality in cache. And the last part, after the break, I want to talk about some other techniques where once you've already changed your algorithm, and if you're a hardware designer, how can we make it more efficient to access memory as well? Okay, we'll take a quick break. All right, so before we start the next part of the lecture, I wanted to introduce some terms. I'm just trying to find some pictures. So this is, it's probably a fake picture, but it's a picture of Apple's A10 processor. Now this is not actually the processor. What you're seeing is the package around the processor. So that's what I was trying to draw here, is that if this is a motherboard, I'll have a processor, a chip, and it is in some package. So normally when somebody shows you the chip, you don't see this is the chip, but this is a chip. This is an NVIDIA chip. This is an outside view of the chip of a different chip in a package. And then you can put, so here's a package, here's another package. I guess that's a Broadcom. And then that chip is plugged into a board, and the chip will have pins, and those pins connect to wires to traces along the board, which will go out, and at this point, like there's DRAM here. So if you open up your desktop computer, you will see a CPU package. Usually there'll be a big heat sink on top of it. It will plug into your motherboard. There'll be a bunch of pins connecting to board wires. And those board wires, in fact there'll be 64 of them, for a 64-bit memory bus per channel, will connect up to a DRAM. So that's, here, there's an example of a motherboard. Do I have anything else? I think I'm lacking good pictures. This is a chip. That's the silicon itself, not a package. That's a chip. Okay. So, back to the lecture. So, if moving data is expensive, and one answer is, well, let's move less data by changing our code. Let's access data in on-chip memories as much as possible. Another solution is, well, if moving data is expensive, well, let's move data less far. Let's try and bring memory closer to the processor so we don't have to move it all the way over here every time to burn all this energy. In other words, if your best friend lives in another city far away, and you're always traveling to visit each other, well, at some point you might say, hey, let's move closer together. So one simple way to bring DRAM closer to the processor is to take the DRAM and put it in the same package. So take this little DRAM and get it in the package with the same processor. So if you hear the term on-package DRAM, that means that the DRAM is much closer to the processor because it's in the same package. And then there's also embedded DRAM. So some high-end Intel processors will have embedded DRAM, and the Xbox 360 had embedded DRAM. And so that's DRAM right next to the processor, sometimes in the same package, sometimes actually maybe even close to the same chip. And this DRAM, for example, can give you 50 gigabytes per second read and 50 gigabytes per second write, and it's almost like an L4 cache. Yeah, it's almost like a 128 megabyte L4 cache. So one answer is to bring the DRAM, starting to bring it closer. Now this is starting to get a little bit old. In the last year or two, what you're starting to see is something that looks more like this. So this is the package. This is the casing around the processor. And these bumps here, this is the connection to the motherboard. So the technology that has come online in the last couple of years is the ability to start stacking chips on top of each other. So what you're seeing here is a new type of DRAM, where the DRAM chips, so before I told you like there was a DIMM where there were 8 chips laid out like this. Now the chips are stacked right on top of each other. So here's a bunch of just DRAM chips. And the technology that has come online recently is this idea of being able to run the wires not on the outside of the chip, but through other chips. And as you can imagine, if you have a chip Well, the area is much larger than the perimeter, right? So if you used to only be able to have data pins on the edge, now you can have wires reading data out of the DRAM arrays straight down through. And those are what's called through silicon vias. So via like a road, and through silicon meaning that they're going directly through the silicon. So you can have a lot of these through silicon vias that are connecting up to row buffers in all of the various DRAM chips. And now this through silicon via has also done something really nice, is that, so I have all these DRAMs, and then I have a chip at the bottom which is called the interposer. So what I've done is I put all of these DRAMs on a chip, and then I actually put the processor on the same chip. So the memory bus now aren't wires over the board. The memory bus is actually just a chip. So there's one chip, and I stack the processor on top of it. And then I stack the memory over here on top of the same chip as well. So this chip is just serving to be the memory bus. And I can run a lot of wires through a chip. So there's a very, now the CPU and the memory are stacked on the same chip inside the same package. And there's many, many wires connecting the memories to the processor. So there's a much higher bandwidth connection to memory. We haven't gotten to the point yet where they've decided to take the memories and stack them on top of the CPU itself. And the reason is, I think there's a couple of reasons. Some of them are just, some companies make DRAMs and other companies make processors, and so nobody makes both DRAM and processors. But another challenge is processors generate a lot of heat. And currently the heat goes up, and the fan blows it off. And if you cover up the top, the exhaust, essentially, with a bunch of DRAM, it's going to get very hot. So they're very worried about how to cool these things. So if we look at these designs, here's kind of what they look like, and they're all pretty new. So in 2015, AMD built a graphics processor with a 496-bit memory interface. So it's a 512-byte memory interface. So it had 4 of these chips with a 1024-bit interface, not 64, 1024-bit interface to memory. Here's NVIDIA's P100, which is 2016, and again, here's the block diagram of both of these. There's this really big chip called the interposer, which is kind of like the thing that everybody puts their silicon on. The GPU goes right here, and the various stacked memories are right on the same chip with the processor. And each of these stacked memories has 1,024 wires to the main CPU. So this latest, for example, is NVIDIA using 4 stacked memory chips, has 4 times 1024-bit interface to memory. So it has a 720 gigabyte per second interface to memory. And notice that like the computers that we just bought at CMU, remember it had 70 gigabyte per second interface to memory. That is a lot of bandwidth. So it's getting close to a terabyte per second access to these 4 stacked memories. And those 4 stacked memories are about 16 gigabytes. So you can have 70 gigabytes per second access to normal DDR4, so hundreds of gigabytes of memory at 70 gigabytes per second. And for 16 gigabytes of that memory, you can get to it at 720 gigabytes per second. And Intel's processors for supercomputing have some of the same things. So here's that Xeon Phi processor with 72 cores. And they also have in-package stacked DRAM right next to this thing. 16 gigabytes as well. And these on-package DRAMs are about 5 times the gigabyte, the bandwidth of DDR4, so that would be roughly 70 times times 4, so it's like 300 gigabytes per second. Okay, so one answer was let's move the memory closer to the processor. Make it really, really quick to get to memory. Another answer is how about we move the processor into the memory? Let's go the other way. So for example, imagine you are going to do a search, right now. You open your phone, you take out your phone, you say, okay, I want to run a computation, and the computation is I want to search Baidu for some information. Okay, so how many people think that the search works by Baidu sending you their database, you read the Baidu database, and you search it on your phone? That would be very silly, right? You would move all of Baidu to your phone, and then we can load and store the data. That's not what happens. So what actually happens is, well, the search, the definition of the problem, the computation, you send to Baidu. They perform the search right next to their servers, and then they send you the results. Right? So nobody would ever think about implementing a website by moving all of the data on the website to your processor and then performing the computation. We always move whatever you want to do. We send a command to the website, and it gets executed on their servers. So let's think about a little bit, so with that in mind, let's think about what does a computer do when we do something as simple as memcopy. Let's say you call memcopy, and computer programs use memcopy all the time. We copy bytes of data all the time. So let's say we have some source buffer and we want to move it to this destination buffer, memcopy source dest. Well, memcopy is going to load the data in the source buffer, load it into a register in the processor. It's going to bring it in the L2 cache, bring it into the L1 cache, load it into registers. And then it's going to store the data in registers out to new value in memory. So it's going to vect it, it's going to update L1, L2, and all the way out to the destination buffer. No computation is ever performed, but all the data went from the DRAM array into the processor, and then all the way back out to the DRAM array. So recently, some people have been trying to say, well, for simple operations like moving data, why is a processor doing that? Why isn't memory why can't I send a command to memory which says, please move this data from here to there? And now that you know how DRAM works, you can think about some very easy ways to do that efficiently. Like, for example, we know that if we want to read 2 kilobits of data all at once, in 10 nanoseconds we want to read 2 kilobytes of data, well, we know we can activate the row and read that data down into the row buffer. Well, why not just now activate a new row and store the data in the row buffer back into that row? So now I can do a 2 kilobit memcopy without involving the processor or moving data over the data bus at all. Because here I can move 2 kilobytes of data at a time. I have 2,000 wires. If I move the data to the processor, well, first of all, I have to move it over 64 wires, move it really far, and then I move it right back into a different part in the DRAM. So people are starting to experiment with slightly smarter DRAMs that can do a little bit more, so that we don't have to involve the process. Another idea would be data compression. If it's expensive to move data, we should compress it and move less data. And so we compress data all the time, we call zip, but your programs probably don't actually run on data that's compressed in memory very often. Usually it's decompressed by the time your program is running. But processors have a lot of instructions to help assist you with storing data in compressed form in memory and decompressing it after it goes over the memory bus. Like, for example, here's an instruction that loads an 8-bit value from memory. So it loads 1 byte, but then upconverts it to a 32-bit float. It does a fixed 0.8-bit conversion two 32-bit floating points. So the 8-bit is a number between 0 and 255, or we can interpret it as a number between 0 and 1 in fixed point. Well, normally you'd have to burn a few instructions if you loaded that byte to convert it to a floating point number. It's not too cheap to convert fixed point to floating point. So this is an instruction that does it for you all, I think, in one clock. So it says, load 8-bit values and convert to 32-bit floating point values. And it does it for, it's an MMX, sorry, it's an AVX instruction. So it can do it all on a vector of elements all at once. Like, for example, imagine reading 8 pixels, which are chars, 8 bytes, from an image, but you want to do math, and you want to do the math in floating point. So this saves you all the trouble of having to convert it yourself. Another idea that's starting to gain more interest is cache compression. So what if the cache, because the cache is pretty small, what if the hardware compressed the data in the cache for you so it could fit more data in cache? So this is a little bit interesting now, because now that the hardware is like compressing the data for you without ever knowing. You don't know. Your program just reads these values, and the cache may compress them, transfer them over the bus compressed, and then decompress them only when you access the data. So coming up with a compression scheme that will work in hardware is pretty tricky. It probably needs to be pretty simple. You don't want to implement all of gzip in hardware. And it has to be really fast. Because remember, the whole point of keeping data in the cache is to access it with low latency. So if you access it, and the cache said, well, hold on, I need to decompress it first, wait, that's not so good. It defeats the benefit of the cache. So let me give you one starting example. Let's say that we're going to assume the values next to each other in memory are about the same value. They're similar values. So we can compress all of these values in memory by picking some base and then not storing the full 32-byte values, but let's just store the difference between the base and the next 32-bit value, as 1 byte, right? Because all of these values are within 1 byte of the base. So I can encode, let's say, a whole cache line, 16 4-byte numbers, as 1 4-byte number, followed by 15 more bytes. So I can compress 64 bytes, 16 floats, 16 integers, as 1 integer plus 15 bytes. So I can go from 64 bytes down to 19. So now my cache, I can fit almost 4 times or at least 3 times more cache lines. It's like I have 3 times bigger cache. That's really kind of interesting, right? So here's a question for you. Here's a puzzle. How would you pick what the base should be if I gave you a list of 16 numbers? So I gave you 16 numbers. They're all 4 bytes. That's 64 bytes. That's a cache line. And you want to compress it, so you probably want to find a base that's really close to a lot of the other numbers. What would you do? And you have to do it really, really quickly. What are some ideas? What base would you like? So what do you think this picture is suggesting? What might be a good base? The what? So one idea is I could take the average of all the numbers, because that's probably pretty close to some of them. But okay, so that might be a good base, but now I have to add up all the numbers. I now have a computation that has so I have to probably do a combining tree to add up all the numbers, right? And so if I want to compress this cache line, it might take a while to find the base. So I have to do some math, and I introduce latency. So what's a simpler? Well, there are other answers. Some may be more or less simple. So one was average. I could also take the min or the max and hope that the min or the max is close enough to the rest. What about any simpler ideas? What do you think?
The most common number.
The most common number, yes. So all of these require me to look at all of the numbers. Min and max are a little bit simpler because I only have to do a min operation, not an averaging operation. I don't have to divide. Take the mode, the most common number. That's interesting too. Then I only have to compare, at least. What if I don't even want to bother looking at all the numbers? Yeah, I could randomly pick a number. What's even simpler than randomly picking a number? How about pick the first number and hope for the best, right? So there are a lot of different options, right? So you can use the first word in line and then hope that works. And if it doesn't work, oh well, like it's a hardware solution. But let's look at this pattern. So let's say that we use this idea. Does this cache line compress very well? Let's say we use the first word in the line, number in the line, or maybe even the last number in the line, or maybe we use the average, or maybe we use the mode, the most common number. We can take anything that we discussed. In fact, the average is probably really bad here because none of the numbers are close to the average. First or last. So what's the problem? And in fact, this is not uncommon because think about what this is. This is a pointer and some data, and pointer and data. No, wait, this is This is like data and then a pointer, some more data and then a pointer, some more data and then a pointer. This is basically a linked list with 2 integers per node, right? So this is not an uncommon pattern in computer science at all. Because you have pointer data, which has really big numbers, and you have usually like fields in a database or something, which are small numbers. What would be the compression here? Why don't you talk about it for a second with your friend? What would be your compression scheme for this particular, I'll give you maybe 30 seconds or a minute to talk about it. Or in other words, I'll say, well, if one base is not enough, it's pretty obvious that you want 2 bases now, right? You either want to compress every number as an offset of this, or you want to compress every number as an offset of this. But how do we find these bases? Now it's a little bit trickier, because I need to find 2, the right 2. Okay, what do you think? Spirit of being simple. How do you find the two bases in this example? Does anyone want to propose a starting idea, and then we can try and make the idea better? What did you think?
The maximum one and the minimum.
Okay, so the first idea is maximum and min. That requires me to look, and that would be perfectly reasonable. And that requires me to look at all of the data first. Okay. Does anybody have any other solutions? Because the max and the min may not be the best answer, actually, right? Because I can have a bunch of data right in the middle, and then one value really big and one value really small. Any other thoughts? What did you guys think? So I'll give it an individual. How about the first one and the second one? It's an answer. Or the first one and the last one. Now what's the problem with that? The problem with that is if the first and the second number are about the same, then that's about as good as one base. Right? So I need to somehow kind of look over all the data to figure out that there's something far enough away. And then the other problem here is now my compression is not as good, right? Because I have to store two full values, not just one. Before I only had to store one full value, one base, and then I could have like the offset. Now I have to store two full values and offsets, and I also need a bit per element to tell me which is the base. Well, here's an idea. Like this is what really, people that like to optimize code start thinking about. So the first person, one idea was saying, hey, we're going to store two bases, but one of them will always be 0. One base is always 0, so I don't even have to store it. I get one base for free. And then the other base should be the first item that doesn't compress well as an offset of 0. So the scheme that somebody says, well, first of all, we're always going to assume that 0 is a base, because that's very common. And if we assume 0 is a base, we don't even have to burn 4 bytes to store the number. Then we're going to compress all the data in the cache line with 0 to figure out what the offsets from 0 are, which difference from 0 is not a mathematical operation. It's pretty easy, right? So you just need to look to see, well, which values are greater than a byte. And for those values, I'm going to take the first one and use that as the second base. So attempt to compress with 0, compress the remaining numbers that don't compress well with 0, using the first number that does not compress, that's far enough away from 0 to not compress well. And so this compression scheme was called base delta immediate, which means immediate is 0. So it's called BDI compression. And these are the results from their paper. It's a pretty recent paper, 2012. And every one of these bars is a different algorithm, a different program. And these various bars are different numbers of bases. So the student, the PhD student, was like, I wonder how many bases I need. What's best? 1, 2, 3, 4. How many bases is best? And so that's what you see here. Is he ran the experiment of how much compression that can he get if he allows the compression scheme to use 1 base, 2 base, 3 base, and so on and so on. And what do you know about the result? What do you notice about the results? So this is the amount of compression. So bigger is better. Higher compression ratio is better. Look what happens. Up, better, 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 down. Better, 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 down. So it goes up because, well, 2 bases is better than 1 in general. But then it starts to go down. And why do you think it goes down? Because, well, if I'm storing so many bases, I have very little room to continue to compress the data, right? And so it starts to go down after a while, back to no compression. So this is, on average, he was able to get about 1.5x compression with his 2 bases, where one of them was 0. And that translated into about 10% faster performance, because the applications had more cache hits. Now, if you think this is sort of kind of fun and crazy, all modern GPUs, when they're rendering graphics, not when they're running CUDA, when they're rendering graphics, do really crazy compression on the image that they are creating. So here's another example, which is exactly like what I just showed you, except it's actually in 2D. It's compressing an image, assuming that the cache line is a 4x4 block of pixels from the image. So now the image in memory is laid out, and these are consecutive addresses, even though the whole row of the image is much longer. So the image is not stored row major in the address space. So they look at all the values, and they say, well, if I look at the world, like there's a lot of similar values if it's close to each other in X. Or it's a lot of similar values if it's close to each other in Y. And in fact, most of the world came from geometry that were planes. So let's just assume that these 16 pixels came from a plane. So they take the top left corner, or any pixel, and that's the base color. And then they compute how much the color changed, 1 pixel to the left, delta x, and how much the color changed 1 pixel down, delta y. And then they extrapolate the rest of the values. So they say, well, if this color was gray, and this color was a little bit lighter, well then probably this is a little bit lighter, and even more light, and so on and so on. So if every pixel here has coordinate ij, then the value is base plus dx times I plus j times dy. So the compressor is a predictor of what all the other values should be. And then if the prediction is wrong, then they store the offset from the prediction. So I think in this particular example, I don't know if I have the bit sizes, but we might, let's say that all of these pixels are 8 bytes. Or sorry, are 8 bits, like just 0 to 255. It's a grayscale picture. Well, they will store the original base as a byte, and they might store the dx and dy's as a full byte, or maybe even 4 or 5 bits. And then this particular scheme stored, I think, every correction as 2 bits. You got 2 bits to correct the prediction. So that's an example of if you know what your data actually is, if you know it's an image, the hardware is actually doing even more compression for you as well. And just to show how crazy this is getting, here's an example of a technology that ARM, that makes GPUs, mobile GPUs, consider doing. Now, I don't know if they're actually doing this, but they wrote up a publication about how this works. So imagine you're rendering a game. You're playing your favorite game. And every frame, the image doesn't change very much. In fact, if you're playing like a game where the output is like a cartoon, most of the pixels are very much the same from frame to frame. So what their memory controller does is that whenever you decide to store a cache line's worth of pixels, they compute the hash of the cache line. And they remember the hash code for all the pixels in the cache line. So out in memory is the real data, but in cache is stored the hash of all of the pixels in memory. Now in the next frame, when you go to write the exact same part of the screen, you do all the computation to figure out what color the pixels should be. And then you compute a hash of the new values. And if the new values hash the same value as the old values, you assume it's the same color, and then the implementation of store is do nothing. And so this is showing that with the screen is moving very, very slowly, almost all of the pixels on the screen don't change from frame to frame. And even if the screen is moving really fast, like it's an interesting side-scrolling game, sometimes almost 50% of the pixels still don't change. So this was a technology that they considered for their GPUs which was to say, remember what the value in memory is, detect when you are storing the same value, and if you're storing the same value, just skip the memory write altogether. Just give up on it to save the energy. This was all about saving memory bandwidth. So this whole so we talked about a bunch of techniques to try and be more efficient about memory. All throughout the class, we've talked about changing your algorithms to access less data, improve locality, hit the cache. Today, I talked about a number of new hardware architectures that give higher bandwidth to the processor. And I also talked about hardware architectures for compressing data. And I also talked about hardware architectures that try and move the computation into the memory so that the data doesn't have to move all the way back to the processor. So I promised you that I would be a little bit shorter this time, and that I exactly am shorter. So I will save you 8 or 9 minutes today. But that is all for the lecture. For those of you that are interested, I will show you one fun little thing that I didn't. These are in the graph DSL lecture slides. Is that data compression is really important when you're doing graph processing, very much like your assignment right now. So your assignment right now, nobody is going to be able to get a perfect speedup. And you're not going to be able to get a perfect speedup because you are bandwidth bound. So and if you go have fun after you do your assignment, you can go look at DSLs for processing graphs. And you'll be very frustrated because your whole assignment 3 can be done in modern graph processing frameworks in like 10 lines of code. So this is a framework called Ligra. This is the implementation of PageRank. It may be faster than yours. Here's an implementation of BFS in Ligra. It's probably faster than yours. So tonight, when you're done, go Google this system called Ligra. And you can download it. It's really simple. In fact, the student that created it won the ACM dissertation award a couple of years ago. Best PhD thesis in the world. Not for Ligra, but for his theoretical work. But he created this thing. And so this is an implementation of assignment 3, completely parallel in Ligra. And Ligra is an API with 3 functions. One called EdgeMap Sparse, another one called EdgeMap Dense, and so EdgeMap Sparse, EdgeMap Dense, and Vertex Map. So it gives you 3 functions to call, and if you call those functions, you can implement BFS, you can implement PageRank, you can implement many of your favorite graph algorithms, connecting components between a centrality. And PageRank and Ligra will, if you care, compress your graph for you. So in assignment 3, this is how the graph is laid out for you, right? Like, so I give you a list of edges. So vertex ID 32 has all of these edges. So Ligra will do exactly what we just talked about on your edge lists. It sorts the edges by index, which means that the difference between consecutive edge numbers is small. And since the difference between consecutive edge numbers is small, usually they can be represented in 1 byte or 2 bytes rather than 4 bytes. And so the graph is stored in this compressed form. Right? So in this case, if this is my edge list, I compute the differences in the edges, and then I actually group the edges according to how many bytes are needed to represent them. And I store the edge list not as a list of integers, but as a coded thing of saying, here are all the edges that need 4 bytes, here are all the edges that need 1 byte, 2 bytes, and so on and so on. And they're able to compress the graph significantly, given that there's locality in the edges. And for a bandwidth-bound computation, this is helpful. So now I'm going to show you a graph. And I want to know if you can tell me why the graph looks like it does. Because if you can tell me, you are mastering all of the ideas in the course, or some of the ideas in the course. Okay, so here's what it is. Here is running, I can't remember what graph algorithm it was. Oh, no, here they are, different graph algorithms. So here's BFS, here's PageRank, and here's some other Bellman-Ford, connected components, and whatever. Okay, so I want you to look at two things. I want you to look at, so this is the performance, but the amount of time it took to run the computation on one core. And this is, let's say, basic, using the graph representation exactly that I gave you in assignment 3. No compression. So that performance is the light gray, and that's performance 1. Now, let's take this line here, which is this gray bar here. Okay? And this is running the same computation on the compressed graph. And every time you visit a new node, like in BFS, the first thing you do is you load the compressed edge list, and then you write the software, you have instructions to decompress it. And then you walk over the decompressed edge list. So you can imagine how you could change your assignment 3. You would load it in compressed form, you would decompress it, and then you would iterate over all the edges, just like you do now. So first of all, when running on one core, not parallel, what happened between the baseline and using the compressed graph? The runtime went up or down? Went up. So the program got slower. Compression did not help. Same graph now on the right, same programs, same baseline is no compression. Gray bar is with compression. The only difference now is now we're running in parallel on 40 cores. What did you notice? Compression helped. So on one core, compression did not help. 40 cores, on some algorithms, like PageRank, it gave you probably 2.5x faster performance. Why is that? Why does compression help when running the code in parallel on 40 cores, and does not help when running the code on one core? Correct, exactly. On one core, we are not memory limited. We are running as fast as we can, as the core can do instructions. When 40 cores all start asking for data in different parts of the graph, we become memory bound because memory cannot keep up with all of those requests. So it makes sense for these processors that are waiting on memory to instead read less data and burn some of their wasted cycles to do decompression. Because if they weren't doing decompression, they would be sitting there waiting on memory anyways. So it makes sense to do more work, more compute, to make better use of the scarcest, the bottleneck in the system, which in this case is memory. And in this case is the processor. So more work slows you down. Here, more work speeds you up. Okay, I'll stop there. You will like Ligra if you liked assignment 3. And I think it'd be fun if you want to download Ligra. BFS and PageRank solutions are in the example code. And you can run it on the same cluster, and you can see if you beat Ligra. You probably maybe a good solutions to assignment 3 will be about the same. But of course, if any of the solutions to assignment 3 look too much like Ligra, you will get in trouble.